Dzień dobry Państwu. Dzisiaj będziemy kontynuować wprowadzenie do klasyfikacji tekstów i będziemy mówić na temat naive Bayes i support vector machines. Ja teraz przejdę na angielski. So today we're going to be talking about introduction to text classification and in particular about the naive Bayes and support vector machines ideas for text classification. So as we saw in the previous lecture, the classification means assigning a class or category. So in this picture we see two classes, white and dark, and as we also can see, the classification here is not perfect. And since this is a two-dimensional situation, the classifier is essentially a line. So above the line we have most of the white dots, and below the line we have the dark dots. So for text classification or categorization, the general approach is the following, that we would take a collection of new documents and we would like to get one or more categories or labels for each document plus a confidence number, for example, probability that the document is in the given class or category. And typically we do it by first training a classifier. So our resources are a training corpus and test corpus. So we train on a training corpus and we test on the test corpus. And then when we get new documents, we have some confidence that our classification results are correct with certain expected performance. So this is usually done in 3 steps. So we use a collection of training documents to learn one or more classifiers. We use a collection of test documents to choose the best classifier of the classification method, and then we apply the classifier to new documents. So how do we go about finding a good classifier? Usually we have to prepare the documents, so we need to put them in the right format. So for example, this could be an XML format or a TREC format. We create a dictionary to limit the number of features, and sometimes this is done automatically by the classifier. We create a feature matrix or term document matrix that is based on the dictionary. Again, this can be done by a classifier. And then we experiment with a number of algorithms to see what works. All right? There is no clear picture about which classifiers will be better on which corpora, although we know some estimates of complexity of the classifiers, and we know, for example, that naive Bayes is usually much faster to train than a support vector machine classifier. We will be talking about 4 classes of classifiers. So it starts with probabilistic naive Bayes classifier. We're going to be then moving towards weighted scoring classifiers. And we already talked about logic classifiers, so rule-based classifiers, although we didn't apply it to text. And in the lecture in January, we will also talk about nearest neighbor classifiers. So we're going to look at one example of classification. We mentioned before that text classifier can be used to classify email spam versus non-spam. And in this example, we have 4,600 email messages. The text has been converted to the ARF format, which is a form of a file which is used by the WECA tool for machine learning. And we're going to run a couple of classifiers on this particular set of messages. So we're going to see what works, what doesn't work, and in the process, we're going to learn how this classification is performed. So here's the data, okay, and you will get the copy of the data. It's in the file called spam-base-arf. I already sent a zipped folder of today's and the last time presentations together with this file, so you should be able to experiment with it yourself. And we can see that there is a number of attributes. Okay, not all attributes are shown here, but we can see at the bottom of the attribute list that we have two classes, 0 and 1. And we have some parameters. So going from the bottom, we have how many capital letters are total, the longest run, how many capital letters is on average, okay? And then we have certain other attributes like the number of character sequences, which is like the pound sign or sharp. The attribute, another attribute is frequency of the dollar sign, representing money. Similarly, we have attributes that represent exclamation mark and some other punctuation. And this is in addition to other attributes which talk specifically about words. Okay, so we're going to look at some of these in a minute. And then we have data. So the data is, as I said a moment ago, about 4,600 messages. And what you see here, it looks almost like a term frequency, term document matrix. So we have documents on each row. And for each document, we have the value of the attributes. Okay, so we have, if I remember correctly, 58 attributes, of which the last one is the class. If we start with the 0 classifier, okay, which essentially classifies everything as being in the most frequent class, so we have spam versus non-spam here, and everything, all data is classified as a more frequent class, so obviously this is not a good classifier, but it gives us the baseline. We shouldn't be able to do worse than that by using any of the classifiers we try. Okay, so this gives us so this gives us the baseline, which looks like this, with appropriate F measures. And now let's look at the same data, but classified by the naive Bayes classifier. So as we can see here, we have 1,800 messages which are misclassified, that should be classified as B, and have been classified as A. So in naive Bayes, we can correctly classify 1,700 of these messages, but at the cost of classifying some of the A messages as B, and there is still 88 messages which are misclassified from the B class. This gives us the performance measure that we usually measure as F measure for the first class, for the class 0 of about 80%, and for the class 1 of 78%, so the average performance here for both classes is about 79%. The F measure, if you remember, is computed by multiplying precision times recall, dividing by precision plus recall, and multiplying by 2 to get something that varies between 0 and 1. Okay? And precision has been defined as fraction of retrieved instances that are relevant, so correctly retrieved, and recall is fraction of relevant instances that are retrieved. Okay, so how well retrieved. So obviously this is a reasonable approach. We get some data classified correctly. It's obviously not a perfect approach, but we get about 80% of the instances classified properly. So how does the naive Bayes classifier work? So at the top of the slide, you can see the statement of the Bayes theorem. which talks about the probability of assigning a label to a given document. So the label can be 0 or 1, and we want to express the probability of assigning a label to a document by some prior knowledge. So we could ask for the question, what is the probability of the document given the label, and what is the probability of the label? And we divide the product of these two values by the probability of the document, and we know that this is equal to the probability of the labeled given document because of the base theorem. So the document will be represented as a vector of features. So for example, this could be word counts or counts of certain characters, as we saw a moment ago. And we, to compute this value, okay, so the probability of classifying something as spam or not spam, we will need the following terms. Okay, so we need the probability of the label, we need the probability of the document given label, and we need the probability of the document. There is more than one way of creating a naive Bayes classifier, but the ideas that we're going to be discussing are general, and the main idea of making the independence assumption is common to all this way of naive Bayes classification. So let's just go through it and let's just see, using an example, of how this can be done. So the first thing that we can compute is the probability of the label. This is relatively easy, okay? We just count the number of the documents which are labeled with 0 to get the probability of the 0, and divide it by the number of documents, the total number of documents. So that's the formula that you see at the bottom of the slide. So PL equals number of docs labeled L divided by the total number of documents. So we know how many documents we have labeled as class 0. We know how many documents we have labeled as class 1. So here we're going to be using a simpler example, not with 58 attributes, but with just 4 attributes plus the class value. And we're going to be using, this example comes from the book Fundamentals of Predictive Text Mining by Wise and two other authors. And we can see that we have 2 classes as before. We have 4 attributes or 4 words. And we can compute the probabilities of each class. So we have 4 documents classified as class 1 and 6 documents classified as class 0. With the total number of documents is 10, so the probability of class 1 is 40%, and probability of class 0 is 60%. All right, so that part is easy, and we could do the same thing for the corpus of 4,600 documents that we discussed a moment ago. Now, notice that since this is a binary classification, the probability of the document being given label 1 or being given label 0, the sum of these probabilities is 1, okay, because there are only 2 possibilities and all documents are being classified. Right, so let's continue. So we see that we have computed P of L in the expression on the right-hand side on the top. So we need to compute the next thing, which is probability of the document given label, right? And this is where things become somewhat interesting. All right? So how do we compute probability of the document given label? Well, we do not know what is the probability of the document given label, but we do know what is the probability of the word given label. So, for example, in the table on the right-hand side, we have the probability of the word 1 given label 1 is 75%. And this is the case because in 3 out of 4 cases, the word 1 is present in the document labeled with label 1. For word 2, this probability is lower, it's only 25%. And for word 3 and word 4, the probabilities are both 50%. So we saw before that the sum of probabilities of the documents being given label 1 or label 0, the sum of these probabilities is equal to 1. So the question is, do we have the same situation here? So that is the probability of the word given label 1 plus probability of the word given label 0 equal to 1. Well, the answer to this question is no, because you can imagine a situation that certain words, for example, determiners, or certain symbols, like dollar symbols, might appear in both legitimate mail, for example, I'm getting a statement from the bank, and it might appear in spam offers. Okay, so there is no reason why this probability should be equal to 1. The situation is not mutually exclusive. So the same word can appear in multiple documents, in multiple types of documents, and the probability can be less than 1. And similarly, the word can appear in all documents, like determiner V or determiner A, or some common word like is, and then the sum of these probabilities would be almost 2. So the next question is, why do we care about these probabilities of words given label? Well, the reason is that we do not know what the probability of the document really is. Okay, but we do know that we can compute this probability of the word given label, and words are put together in a document. Yes, so we would like to be able somehow to pass this information about probability of the words given the label to the probability of the document given the label. So the question is whether one can be used to estimate the other. And the answer to this question will be yes, all right? But this slide talks about what we just explained a moment ago, is that while the sum of the probabilities of the labels is 1, the probabilities, there is no obvious relationship between the probabilities of individual words. And the naive Bayes method relies on using collections of words. So we're going to see how we pass from the collection of words to the document. Okay, so that is done using a very simple idea. We assume that creating a document is like playing dice or card. So the probability of getting two words in a document will be simply equal to the product of the individual probabilities. With the analogy that getting 2 and getting 3 in tossing 2 dice is equal to the probability of getting 2 in one toss and getting 3 in another toss. So this is called the independence assumption. Obviously, this assumption is false for documents because certain words appear often together. However, as an approximation, as a model of a document, it works often reasonably well. So let's see in our example how this can be done. So we have probability of word given label 1 and probability of word given label 0 in this table at the upper half of the slide. And as we said a moment ago, we're going to approximate the probability of the document by the product of the probabilities of individual words, right? So the main idea here, main thing to look into in the formula at the bottom of the slide is that we have to take into account both the words that are in the document and the words which are not in the document. All right? So if the word is in the document, we take this probability of the word given label 1. And if the word is not document, we take the complement, so 1 minus probability of the word given label 1. So we will see how this is done on a concrete example of a document. So we have a document consisting of W2, W3, W4, and the question is whether it should be labeled 1 or 0. What do we know? Well, we have the Bayes model and we have the naive Bayes model approximation of the general Bayes formula. So we can compute the probability using the formula we saw in the slide just a moment ago. And let's look at it in detail, okay? So at the bottom of the slide, okay, we have computed, or we have partly computed the probability of giving label 0 and giving label 1 to the document D consisting of words 2, 3, and 4. All right? So since the word 1 is not in the document, so for the label 0, we use the complement, so 1 minus 0.5. And for the label 1, we also use the complement, 1 minus 0.75. Now, other than that, we don't have to use the complements because the other 3 words are in the document. So for the probability, to compute the probability of label being 0, we multiply by 0.67, 0.33, 0.5. So in the third column of the table that you can see here. And for label 1, we take the probability of word 2 given label 1 being 0.25, we multiply by 0.5 and 0.5. All right, so this gives us the probabilities of the document using the naive Bayes formula and the dependence assumption that the words produce the document independently the same way as we get a sequence of integers between 1 and 6 by tossing a dart. Well, we have to multiply it by the probability of the label, and we know it from before that for label 0 it is 0.6, and for label 1 it's 0.4. That's how we get the final formula, except for the division by the probability of the document. We could compute the probability of the document, again, given the naive Bayes formula, but notice that for classification, we really care about whether probability of label being 0 is greater than probability of label being 1. And since the probability of the document is the same in both cases, it doesn't influence the inequality. So therefore, we can safely ignore it for the purpose of classification. If we want some additional information, like what the probability might actually be, we would include this information. On the other hand, because this independence assumption is often false in practice, this probability estimate will not be very reliable. So in practice, we can simply ignore it. All right, so I can leave it as a homework for you to take a look at this computation and conclude which one of the labels is more probable. And as I said before, we do not need probability of the document to decide which label is more likely. In practice, we also want the probability of the document being given label to be greater than certain threshold. So often we would use the additional estimate to get this threshold if we care about this threshold. If we do binary classification, we have to decide yes or no. We can safely ignore it. So this is naive Bayes classifier, and we would like to go to a more general collection of classifiers, forming so-called linear model. And the intuition here is the following, that if we look at the naive Bayes formula, all right, so we have this product of probabilities and product of complements of probabilities. And if we apply the logarithm function to both sides, on the right-hand side, we will have a linear expression. Essentially, we're going to have a sum of certain probabilities. So this is the intuition, to replace the sum of probabilities by general linear function. The actual math is a bit complicated. I am showing it on the next slide. So let's take a look at what's happening here. So probability of a class given a document can be rewritten in this strange fashion that you can see at the top of the slide. The xj is the value of the jth attribute. So here we assume that it's a binary classification. If we do that, then we can apply the logarithm formula to the right-hand side, except for the probability of the document, which we take at the beginning of the expression. And then we're going to get this linear expression in the 3.5, saying essentially that this is the e to the power, so the exponential function, e to the power wjxj plus b, where the weights wj are given by the ratios, by the logarithm of the ratios of probabilities, and the b, the bias or the intercept, is given by this sum of probabilities. Okay, so this is a general passage from one to the other. You can try to do the computation yourself. Just keep in mind that you have to consider two cases, one when xj is 0 and one when xj is 1. And you can see that this works reasonably well. For when it's 1, certain expression simplify. When it's 0, the right-hand side of the expression probability of xj equal 1 under c divided by the same equals 0 under c in the power of 0 is equal 1, so we can simply ignore it. So this is the main idea behind the computation, and feel free to do this computation on the side. So what does it give us? So this model, for example, if we want to predict the value, of whether the document is in a given class, we can say that, say, a class has certain score, and if the score is above, say, 1, then the document should be classified as given class. So in this case, we have a class that can be named as earnings, company earnings, and we have a model in which we have features. So we have words like dividend earnings, 8 extraordinary, Rose split York, and then we have weights which can be positive and negative. And the idea is that essentially we add these weights and we get a score, and in this case the score is 1.5 almost, and therefore this would be classified as earnings. Okay, so all words in our dictionary would have a score. Some scores can be positive, some can be negative, and given a new document, we just treat it as a bag of words and assign a score by summing. So this is the linear model. We are adding, we are not multiplying. All right, so let's look at this model from another perspective. So before we talked about classification as having to do with separating points in a space, or in a hyperspace if we have more than 3 dimensions. So let's look at this situation. So here we have 2 classes, red and blue, and obviously they can be separated by the line. So the question is, how can we go about computing this separating line? So the line has certain parameters. So we know that it will be negative slope. Okay, so the first question mark in the expression y equals question mark x plus question mark, we know that it will be negative, but what should be the value of this line, right? And then what is the connection between the parameters of the line and the dots? Okay, so that's essentially what we want to establish. So if we look at the line like y equals minus x plus minus 0.5, okay, we can represent it as a vector, yes? So we can represent it as a vector minus 1, minus 1, minus 0.5, because we can put the y on the right-hand side of the equation, and essentially we have the expression minus x, minus 1x, minus 1y, minus 0.5, linear function, linear expression of these 3 parameters. So we have the vector minus 1, minus 1, minus 0.5. So this is our representation. So now let's look at the classification. So the classification that we want to perform is given as a linear product of the values of the document, representation of the document X, times the weight. Okay, so we have the expression is the sum of Wj times Xj plus the bias B. Right, so let's look at these dots. So if we look at the dots, okay, so starting with the red dots and going clockwise, starting with the blue dot above the red dot, okay, we can look at the representation of the dot. Okay, so the representation of the dot is minus 1, 1. All right. If we want to compute the value, what do we get? Well, we're going to get the value minus 0.5 for the next dot. For the dot 1, 1, we get the value minus 2.5, and for the blue dot 1 minus 1, we get the value minus 0.5. On the other hand, for the red dot, we get the value 1.5. So we can see that we can use the line, we can represent the line as a vector that we saw a moment ago, so minus 1, minus 0.5. And then we can perform the classification using this formula where we take the inner product of the weight vector times the document vector, we add the bias, and this gives us the values, and the values of one class will be positive, the values of the other class will be negative. So this is the idea, right? So it's a very simple method. Notice that unlike naive Bayes classification, we do not assume that the values of the weights have to be probabilities. Okay, we simply take any numbers, and if we can create a classifier that uses bigger number than 1, that is fine, as long as it classifies properly. So the next question is, how do we find the best classifier? So we do it by looking at the margin. So how far is the classifier from one class versus the other class? And obviously, if the line is somewhere between the classes in the middle, this is probably the best. So these are examples of these separating lines. So we can see that line H1 doesn't really do the separation. H2 does the separation but is not optimal, and H3 is a good separating line. So what we are looking essentially is maximum margin hyperplane. So essentially we want the line to be in the middle, or in case we can't really find the linear separator, the line to be almost in the middle between the two classes. Using WECA, we can train the SMO classifier and experiment with classification. SMO is a support vector machine, so the linear classifier, which is optimized for fast learning. And we can see here that the F measure for this classifier is 0.9, so it's almost 10% bigger than the F measure for the naive Bayes classification. So here we got a better classifier. All right? So this was the naive Bayes classifier. So we see the F measure was 7.9, almost 0.8, and here it's almost, it's over 0.9, so it's over 10% difference. All right? So a couple of comments. So there are modifications of naive Bayes that work better, and that they are available with WECA, so you can experiment with them, and that will be your homework. Please run some experiments. The second comment is that the naive Bayes is faster to train than support vector machine classifiers or logistic regression classifiers, which will be the topic of the next. So if there are any questions, we can open the floor for questions right now. All right, if there are no questions, I'm going to say do widzenia i do usłyszenia następnym razem. Dziękuję bardzo.